Hello folks, so this is the second video on the Poisson distribution, but as it says at the top here, today we'll be looking at Poisson approximations to the binomial. So it's looking at the link really between these two discrete distributions. So we're going to be looking first of all at the mean, variance and hence the standard deviation of each of the two distributions. We're going to be looking at the conditions required for approximating the binomial by the Poisson, and then we're going to have a go at solving the problem. So we'll start with the mean and the variance of the Poisson distribution. And if you think about what lambda means, lambda is the average rate of events in a given amount of time. So here it says say per hour. It's the expected number of times we think the event's going to occur. So it kind of follows that the expected value, the average, has got to be lambda. It can also be shown, in fact, that the variance of the distribution is also lambda. And this is quite an important result because the fact that the mean equals the variance in a Poisson distribution can be used to indicate whether a Poisson distribution is actually a suitable model for a particular situation. And we'll have a look at a question like that in a little while. So two results there, expected value of x and the variance of x of a Poisson distribution are both equal to lambda. So if you could just have a go at this question, so just pause the video, try it, and then we'll go through the solution. Okay, so you were asked to calculate the mean and the variance with the given statistics, and then we can use these results to suggest whether a Poisson distribution may be a suitable model. So hopefully you remember back to your A1 maths, and if we want to calculate the mean, then we can just take the sum of x and divide it by n, in this case 100, so that'd be 1.43, and to find the variance, it's the sum of x squared minus the mean squared. So if we do 347 over 100 and subtract the 1.43 squared, we get 1.4251. And if you look at those two results, hopefully you'll notice that they are extremely similar. And we can use that idea to suggest whether the Poisson distribution is a suitable model, because we know for the Poisson distribution that both the mean and the variance are equal. They're both in fact equal to lambda. Well, in this case we can say that the mean is approximately equal to the variance, and hence the Poisson distribution may be a suitable model. Okay, so moving on to the binomial distribution, and hopefully you met these results in your A1 maths. For the binomial distribution, the expected value of x is equal to n times p. So remember, n is the number of trials and p is the probability of success. The variance is equal to npq, and that's where q is the probability of failure, if you like, so it's 1 minus p. So you can use those results to have a go at this question. You're going to end up with simultaneous equations, but perhaps not the sort that you're used to, but you should be able to find the values of n and p. So just pause the video, have a go, and then we'll go through it. Okay, so if we're told that the expected value of x is 4.8, then we can come up with this equation here. We know that np equals 4.8, and the variance npq is equal to 2.88. And with these simultaneous equations, I've labelled them as usual. To eliminate one of the variables, I can actually do equation 2 divided by equation 1. Because here we're multiplying the variables rather than adding or subtracting, so we're going to divide to eliminate, and if we divide this by this, you can hopefully see that we'll end up just with q. So we do 2 divided by 1, and that gives us q equals 0.6. Well, if q equals 0.6, it's fairly easy to find p. It's going to be 0.4. And once we've found p, then we can substitute that into either of the equations. Equation 1 would be easiest, so we've got n times 0.4 equals 4.8, so n is equal to 12. Okay, so the video really is about approximating a binomial using a Poisson. And to do this, I'm just going to have a look at a visualization of these two things. So here we've got it's just a GeoGebra file, but it's showing a binomial distribution in red. So these red bars show a binomial distribution, and at the moment we've got it set that so that n is 100 and p equals 0.5. Okay, and then in blue we've got a Poisson distribution, and it would make sense obviously for us to make sure the averages, the expected values, are the same for each of these. So with the Poisson distribution, if n is 100, p equals 0.5, then the mean of that distribution is 100 times 0.5, so it's 50. So we've set lambda, which is the mean of the Poisson distribution, we've set that equal to 50. Okay, and you can see that while they're a similar shape, it's not a great approximation. In the middle, the Poisson probabilities are much lower than the binomial, and towards the edges, the Poisson model gives us much higher probabilities than the binomial. So it's not a brilliant model. However, if we alter the value of p and start reducing that, you'll see that lambda is changing so that it's always equal to np. Then as it goes down and down, you will hopefully see that these two distributions are actually becoming more and more similar. So when we get down here, you'll see that the differences between the heights of the blue bars and the red bars are actually much smaller. Alright, and so it looks like when p is small, the two distributions are more similar. Okay, and we can keep going down, and they are getting closer and closer together. And we can also vary n, and if we reduce n, then it looks like things are perhaps getting less similar. Okay, and particularly if we have a small value of n and a large value of p, then you'll find that the two distributions are very different indeed. Okay, so to make the approximation a reasonable approximation, really what we're looking for are large values of n and small values of p. So if we go back to the slideshow, what we're saying is that if the binomial distribution np has a large n and a small p, then the distribution, the random variable x, can be approximated by the Poisson distribution with the same mean, so the mean np. Okay, now that's quite difficult to judge. As mathematicians, we want something more concrete for our judgment, so this is the rule we tend to go with. Generally, if np is less than or equal to 10, then a Poisson distribution is a suitable enough approximation. Alright. Okay, so why would we want to do it? Well, basically, this is from days where our calculators wouldn't work out the Poisson and the binomial probabilities for us, and working out this value here would involve n factorial, which when n is large, that's very difficult. All right, whereas this one here, x factorial, is likely to be much lower. It wouldn't be as difficult to calculate. Obviously these days you could do it all on your calculator. Perhaps approximations are not so necessary. Okay, so an example here. It says a call centre sells a magazine. The probability that a telephone call made by the call centre sells a magazine is 0.05. The call centre telephones 100 people every hour. Notice it's going straight into part D, so usually an approximation question will be at the end of another question. Okay, so use a suitable approximation, find the probability that more than 10 people telephoned by the call centre buy a magazine in a randomly chosen hour. Okay, so the first thing to notice is that this is a binomial problem that we've got here, a binomial situation. N is 100 if we're looking at people per hour, which is large, and P, the probability of success here, the probability that they sell a magazine, 0.05 is very, very small. So it suggests that a Poisson approximation is going to be suitable, and we can check that by working out NP. In this case, NP is equal to 5. That is less than or equal to 10, so that is successful in the test we use, and we can say that it's appropriate to use a Poisson approximation. Then we think about what the distribution is. Well, this is our original distribution. X follows binomial distribution with n 100 and p 0.05, and we can say that that's approximated by a Poisson distribution with lambda equal to np, so 5. Okay, we're looking for the probability that x is greater than 10. Well, from now on this becomes a standard Poisson problem, so if it's greater than 10 we want to put that in the form less than or equal to, so that's 1 minus the probability that x is less than or equal to 10, and we can use our tables or our calculator to work that out, and it gives us the answer 0.0137. Okay, so we've covered there the mean and the variance of the different distributions, the conditions for approximating, and we've solved a problem. So hopefully you'll be ready to have a go at some questions in the next lesson. Okay, thanks.